Okay, next is the solar PV system designs. So there are three main solar PV system designs, which are the PV system of the standalone type, and then second one is the grid connected, and the third one is the hybrid system. Okay, so first is the standalone PV system. So a standalone power system, also known as a remote area power supply, is an off-the-grid electricity system for locations that are not fitted with an electricity distribution system. Okay. Standalone photovoltaic systems are designed to operate independent of the electric utility grid and are generally designed and sized to supply certain DC and or AC electrical loads. Okay, as you can see here, these solar PV panels or array will will supply the electricity for the DC load, okay, and also the AC load. Okay. The simplest type of stand-alone photovoltaic system is a direct couple system. So this is the direct couple system, where the DC output of the photovoltaic module or array is directly connected to the DC load. Okay. Since there is no electrical energy storage batteries in direct couple system, the load only operates during sunlight hours, okay, making this design suitable for common applications such as ventilation fans, water pumps, and small circulation pumps for solar thermal water heating systems. Okay, and then this one is the first application, and then the second part is the solar PV array provides electricity for the AC loads. Okay. So while a major component and cost of a stand-alone PV system is the solar array, several other components are typically needed. This include, as we can see here, we have the batteries, okay, and then the charge controller, the fuses, and also the isolation switches, the inverter, and also all the wirings. Okay. Okay. Now we look on to the major component that are needed for the PV system. Okay, first is the batteries. So batteries, this one, batteries. So batteries are an important element in any stand-alone PV system, but can be optional depending upon the design. Batteries are used to store the solar produced electricity for nighttime or emergency use during the day. So depending upon the solar array configuration, battery banks can be of 12 volts, 24 volts, or 48 volts, and also many hundreds of amperes in total. The second one is the charger controller. So a charger controller regulates and controls the output from the solar array to prevent the batteries from being overcharged or over discharged by dissipating the excess power into a load resistance. Okay, so charger controllers within a stand-alone PV system are optional, but it is a good idea to have one for safety reasons. Okay, then we have the fuse here. Okay, we have the fuse and also the isolation switch. These fuse and isolation switches will allow PV installations to be protected from accidental shorting of wires, allowing power from the PV modules and system to be turned off when not required, saving energy and improving the battery life. Okay, and then inverter. So the inverter can be another optional unit in a standalone system. So basically inverters are used to convert the direct current, which is DC power from the solar array and batteries into an alternating current AC electricity and power either of 120 VAC or 230 VAC for use in the home to power AC based appliances such as TVs, washing machines, freezers, and etc. Okay, and then finally is the these are all the wirings. Okay, so wiring. So wiring is the final component required in PV solar system, and is very important for this system. Okay, the cables need to be correctly rated for the voltage and power requirements. Okay. Okay, next is the PV grid connected system. So you can see these figures. Okay, these figures. So grid connected PV systems have become increasingly popular for building integrated applications. They are connected to the grid via inverters. So you can see here we have the inverters. Okay, this is the solar PV panels or array, and connect with the inverters. Okay, which convert the DC power from the solar PV panels or array into AC electricity. Okay, so in small systems, as they are installed in residential homes, the inverter is connected to the distribution board. Okay, from where the PV generated power is transferred into the electricity grid or to AC appliances in the house. Okay, you can see here household socket. So this one is for your appliances. And this system do not require batteries since they are connected to the grid, which acts as a buffer. So you can see here it connects to the grid and also from the solar PV array. Okay. Okay, this is the figure on how a solar PV system works at residential house. So first, you can see here, first is solar PV modules will convert the sunlight, okay, from the sunlight to DC power. So it will produce DC power, okay. And then we'll go to the inverter. So inverter, the purpose of the inverter is to change the solar DC power to single phase, which is 230 volt for in Malaysia, alternating current AC, suitable for our household appliances and feeding into the grid. Okay. The third is our house uses electricity firstly from the solar PV, okay, solar PV modules, with additional demand supplied from the grid. Okay, this one for the grid. And number 4 is a meter measures your our electricity production and consumption. And then number 5, any excess power is fed into the electricity grid. Okay, so this is on how a solar PV system works in the residential house. Okay, so the third one is the hybrid system. So hybrid system consists of the combination of PV modules and a complementary method of electricity generation such as diesel, gas or wind generators. So you can see here in this figure, we have fed from the solar farm and also the wind farm. So we connect it together. That's why we call as a hybrid system. Okay, and then the environmental considerations for this solar power. Okay, solar power considered to be one of the most environmentally benign methods of generating electricity. Okay, neither solar thermal nor solar power plants generate any atmospheric emissions during the operation. So a PV installation makes no noise either, and a solar thermal plant very little. Okay. Okay, this is the tutorial for this series. So first, you have to describe two methods can be used to harvest energy from the sun. Okay, And then second, differentiate between the solar thermal and photovoltaic for electricity generation. Third, discuss the limitations solar energy. And fourth is you have to explain the potential of solar energy in Malaysia. Okay, next is the distributed generations or DGs. Okay, so we have covered for this chapter 2 from the introduction, conventional power generation technologies, renewable energy sources, and now is section 2.4, which is distributed generations DGs. And after this is 2.5, economics of power generation. Okay, so first we look on to what is distributed generations. Okay, distributed generation DGs refers to a power supply system where small generating units are installed close to the source of demand. Okay, so if you look on to the system, if there's a power supply that is installed close to the demand, so we call it as a distribution generation or DGs. So these DGs can improve the stability of the overall transmission and distribution network. Okay, and also it reduces the needs to upgrade the transmission system as the power supply system is located near to the source of demand. So example of DGs which is the fuel cells, the solar and wind power. Okay. So this is the figures on the today's electricity and tomorrow's or in future's electricity. Okay, so you can see there. So distributed generation. So you can see in this one for the today's electricity, basically the electricity is coming from the conventional power plant. Okay, but for the in future system, you can see there's a distributed generations. For example, there's a wind farms here and then photovoltaics. Okay, so this distributed generation or DGs may serve a single structure such as home or business, or it may be part of a microgrid, a smaller grid that is also tied into the larger electricity delivery system, such as at a major industrial facility or a large college campus. Okay, so when you connect the electricity utilities lower voltage distribution lines, distributed generation or DGs can help support delivery of clean renewable power to additional customers and reduce the electricity losses along transmission and distribution line. Okay, you can see here lah. So this one is the previous electricity system, which is the centralized power supply from the conventional power plant, and this one in future electricity system will offers more clean and more clean power, which is coming from the distributed generations. Okay, next is section 2.5, economics of power generation. Okay, a power station is required to deliver power to a large number of consumers to meet their requirements. While designing and building a power station, efforts should be made to achieve overall economy so that the per unit cost of production is as low as possible. This will enable the electric supply company to sell electrical energy at a profit and ensure the reliable service. Okay. So the problem of determining the cost of production of electrical energy is highly complex and poses a challenge to the power engineers. Okay, there are several factors which influence the production costs, such as cost of land and equipment, depreciation of equipment, interest on capital investment, and etc. Okay, so in this chapter or section, we will focus more on the economics of power generation. Okay, so the economics of power generation is the art of determining the per unit. For example, 1 kilowatt hour cost of production of electrical energy. Okay, so the economics of power generation has assumed a great importance in this fast developing power plant engineering. A consumer will use electric power only if it is supplied at reasonable rate. Okay, therefore the power engineers they have to find convenient methods to produce electric power as cheap as possible, so that consumers are tempted to use the electrical methods. Okay, so we look for this economics of power generation. We will look on to the cost of electrical energy. Okay, so there are three parts of the total cost of electrical energy generated, which are the first one is the fixed cost. Okay, you can see here we have the fixed cost, semi-fixed cost, and running cost. Okay, we look on to one by one. What is fixed cost? So fixed cost, it is the cost which is independent, okay, independent of maximum demand and units generated. So the independent of the maximum demand and units generated, we call it as a fixed cost. So the fixed cost is due to the annual cost of central organization, interest on capital cost of land, and salaries of high officials. Okay. And then the second one is the semi-fixed cost. Semi-fixed cost is the cost which depends upon the maximum demand, but it is independent of units generated. So the semi-fixed cost is directly proportional to the maximum demand of power station and is on account of annual interest and depreciation on capital investment of building and equipment, taxes, salaries of management and clerical staff. Okay, so the maximum demand on the power station determines its size and the cost of installation. So the greater the maximum demand on the power station, the greater the size and also the cost of installation. Okay, that one is the semi-fixed cost. And the third one is the running cost. So it is the cost which depends only upon the number of units generated. So the running cost is on account of annual cost of fuel, lubricating oil, maintenance, repairs, and salaries of the operating staff. Okay, since these charges depend upon the energy output, the running cost is directly proportional to the number of units generated by the station. So, in other words, means that if the power station generates more units, therefore it will have higher running cost and vice versa. Okay. So, we look on to this equation. Okay, the expression for the cost of electrical energy. Okay, so the cost of electrical energy is equivalent to the fixed cost plus with the semi-fixed cost plus with the running cost. So A plus B times kilowatt plus C times kilowatt hour. Okay, A is the fixed cost. Okay, so A is the fixed cost, B is the semi-fixed cost, and C is the running cost. So this is the explanation on each of the costs. Okay, right. Okay, in economics of power generation, it is important to make sure high load factor. So what is load factor? So load factor is the ratio of average load you divided by the maximum demand. Okay, so that is called load factor. Okay, so if the system have a high load factor, therefore it can reduce cost per unit generated. So a high load factor, okay, reduce the overall cost per unit generated. Number one. Okay, so second importance things is it can reduce variable load problems. A high load factor reduce the variable load problems at various times. Okay, so that is the importance of the high load factor. Okay, now we look on to the example 2.3. So a generating station has an installed capacity of 50,000 kilowatt and delivers 220 times 10 to the power of 6 kilowatt hour per annum. This one is the units generated per year. Per year. Okay, so if the annual fixed charges are 160 ringgit Malaysia per kilowatt install capacity and running charges are 4 cents per kilowatt hour, so determine the cost per unit generated. Okay, so this is the solution of example 2.3. First, you have to calculate what is the annual fixed charge. Okay, so annual fixed charge is given that ringgit Malaysia 160 per kilowatt, so you have to times with the plant capacity. So it gives that the plant capacity is 50,000 kilowatt, right? So you just cancel out here, then so RM 160 times 50,000, so you got RM 80 times 10 to the power of 5. Then you have to calculate what is the annual running charges. So annual running charges is equivalent to 4 cents because this one, the unit is 4 cents per kilowatt hour. Okay, so you have to times with the unit generated per year. This one, the unit also per kilowatt hour. Then you will get 88 times 10 to the power of 5. Okay, and then you have to calculate what is the total annual charges. So the total annual charges is, before this, as I mentioned before, total annual charges is the fixed charge plus with the running charges. So in this example, there is no semi-fixed charges. Okay, so this is the total annual charges. So you just plus them, and then you get RM 168 times 10 to the power of 5 for the total annual charges. So after that, you can calculate the cost per unit. Okay, the cost per unit is the total annual charges. You divide it by the units generated per year. Okay, so cost per unit is total annual charges divided by the units generated per year. Then you'll get the cost per unit, which is 764 cents. Okay. Okay, next we look on to the example 2.4. Generating station has a maximum demand of 50,000 kilowatt. Then calculate the cost per unit generated from the following data. First is the capital cost is RM95 times 10 to the power of 6. Okay. And then the second one is the annual cost of fuel and oil, RM9 times to power 10 to the power of 6. And then taxes, wages and salaries, etc. is RM7.5 times to 10 to the power of 6. And then interest and depreciation around about 12%. And also the annual load factor 40% and also 55%. So you have to calculate what is the cost per unit generated. Okay. But before that, you have to identify the types of charges for each of the data. Okay, for example, the capital cost. Okay, the capital cost is the fixed charges, and then the annual cost of fuel and oil is the running charges. The taxes, wages and salaries, etc. is running charges. And finally, the interest and depreciation is the fixed cost. Okay. So this is the solution for example 2.4. So first we have to identify what is the units generated per year. Okay, which is the equation is maximum demand times with the load factor and times with the hours in a year. So 50,000 kilowatt is for the maximum demand. You times with the refer to the questions, which is 40% for the load factor. So it is 0.4, and then you have to times with the 8,760, which is hours in a year. Okay, so you got 17.52 times 10 to the power of 7 kilowatt hour. And then you have to calculate what is the annual fixed charges. So annual fixed charges is referring to the interest and depreciation, which is 12% of the capital cost. Okay, so 0.12 times the capital cost, which is 95 times 10 to the power of 6. So you get RM 11.4 times to 10 to the power of 6. Then you have to calculate what is the annual running charges. So the total annual running charges is the annual cost of fuel and oil plus with the taxes, wages, etc. So you just sum up all these costs, then you get for the total annual running charges is RM 16.5 times 10 to the power of 6. So the total annual charges is the annual fixed charges plus with the annual running charges. So you get RM 27.9 times 10 to the power of 6. Okay, then you have to calculate the cost per unit, which is the total annual charges. You divide it by the units generated per year. Okay, then you get the cost per unit is around 16 cents. Okay, for this system. Okay, this is the tutorial, so try it by yourself. So given a power plant with capacity of 100 megawatt and delivers 220 times 10 to the power of 3 megawatt hour per annum per year. So if the annual fixed charges are RM 180,000 per megawatt installed capacity and running charges are 3 cents per kilowatt, so determine the cost per unit generated. Okay, so end of chapter 2. Inshallah we will continue with chapter 3. Assalamualaikum warahmatullahi wabarakatuh.